When looking at a double replacement reaction, a double replacement reaction can either be reversible, there can be both a forward and a reverse reaction, or it can be irreversible. If there is only a forward reaction, if there is no reverse, then the reaction is said to be ionic. Now, when you have an ionic equation, you're looking for certain products to be formed. So for a reaction to be ionic, you might want to have a precipitate formed. I'm going to use a down arrow to represent any sort of precipitation. But there are other options. An ionic equation might involve the formation of a gas. And today, in this video, what I'm talking about is the formation of a slightly ionizable product. Now, if we're looking at a slightly ionizable product, the most common example would be water. There's two different ways you could write water. You could write water as HOH, considering it to be made up of an H plus hydronium ion and an OH hydroxide ion. The question is, how does water really exist? So consider this. If you're going to take a shower, what are you showering in? Are you stepping into some acid and some base? Or are you stepping into neutral water molecules? So on my handouts, I'm going to use circling a compound as a way of saying that this does not ionize. It does not break up to form positive and negatively charged ions. Instead, it remains neutral. So if we're looking at slightly ionizable products, the first slightly ionizable product that we would want to talk about would be water. Now, what would be next? Well, let's look at weak acids. We recognize all acids as having H plus, as the positive portion of their formula. And from our solubility rules, we know that all acids are soluble. But let's look at the difference in two acids and what happens to them in water. Both hydrochloric acid and hydrofluoric acid are going to be soluble because they are compounds that are acids. H is in the first family. All acids are soluble. So, if we're looking at putting these two chemicals into water, they will dissolve. Think about something that you know dissolves in water. Before I used glucose, sugar, as an example. You can see the particles initially, but once they dissolve and go into solution, they're no longer visible to the eye. If you could see the particles, look at how different these two acids would look in water. The HCl is going to dissolve in water. How does it exist in water? It exists as H pluses and Cl minus ions. These ions exist with the support of the aqueous media around them. Now, HCl is described as being a strong acid. And strong means that it ionizes completely, 100% ionization. And complete ionization, 100%. So HCl is termed a strong acid. It ionizes, it breaks up to form these ions in water. In contrast, look at HF. According to solubility rules, it too will dissolve. But when it dissolves in water and the particles are no longer visible to your eyes, how does it exist in water? It exists as neutral molecules. These particles do not split up. They do not form ions. Now, this becomes very important later on when we talk about the topic of conductivity. If something is a good conductor, if a chemical is a good conductor, then it must meet two requirements. I'm going to move this down just a little bit. It's going to meet two requirements. To be a good conductor, number one, there must be some flow. I can see flow in this picture. It's in water. When things dissolve in water, they are moving around, they are flowing easily. So there must be flow, and there must be charge. So now we see the difference. HCl is a good conductor. It is a good conductor because it meets the requirements of flow once it's dissolved in the water, and there are charged particles. Weak acids, HF, are not good conductors. Even though they're dissolved and in water, there is no charge. So, the question would be, what are our strong acids? Well, if you look at the periodic table, there's a bit of a pattern. You can start with the halogen family, and there are three strong acids there. These strong acids are HCl, hydrochloric acid, moving down HBr, and then below bromine would be HI. These are 3 out of 5 very strong acids that are easily seen on the periodic table. If you were moving across from the chlorine, you could see another strong acid, H2SO4. Sulfuric acid is a strong acid. And then the next acid that's commonly used in chemistry classes would be HNO3. So we have 5 strong acids, and this is the pattern that they would have on your periodic table. If I had to list a 6th strong acid, it would be perchloric acid, HClO4. But it's not as commonly seen on questions, tests, discussions in a general chemistry class. You need to know your strong acids. So just think about these acids and whether they are weak or strong. Ascorbic acid, weak. Carbonic acid, weak. Hydrofluoric acid, weak. Sulfuric acid, strong. Acetic acid, weak. Acetylsalicylic acid, weak. Hydrobromic acid, strong. You need to know your 5 strong acids. What about bases? Because that's another category. And so, if we are looking at bases, we have something very similar going on. Let's look at some sodium hydroxide. And let's look at something like magnesium hydroxide. Now, we have a different type of problem here. Sodium hydroxide is very soluble, so it is going to dissolve, and when it dissolves and goes into water, it is going to form ions. So we're going to show the sodium ions, Na pluses, the hydroxide ions, OH minuses. Is this going to be a good conductor? Well, remember, what makes a good conductor is flow, it's moving in the water, of charge. Sodium hydroxide solutions are good conductors. What about magnesium hydroxide? Well, here we go back to a solubility rule. Magnesium hydroxide is not very soluble. When it goes into water, it does not dissolve. Instead, most of the magnesium hydroxide is going to appear on the bottom of our beaker in an undissolved state. If it's not going to dissolve, there's no way it can break up to form ions. It is not going to be in the solution. There will be no flow. There will be no charge. It will be a poor conductor. So, even though we could circle magnesium hydroxide, just like we did the hydrofluoric acid, indicating that it's not going to split up and form charged particles, we need to understand that the reason for this is a solubility rule. It is going to precipitate. So for me, either of these will indicate that you understand that magnesium hydroxide is going to be a weak base. Where do we find our weak bases? There are lots of weak bases. So what we want to do again is to list our strong bases. And our strong bases are going to be bases from the first family. This would include things like sodium hydroxide, lithium hydroxide, potassium hydroxide. But we will also include 3 additional hydroxides. They are members of the second family. They are going to be hydroxide forms of calcium, strontium, and barium. All of these ions would have a +2 charge, and so the formulas for the bases would be calcium hydroxide, strontium hydroxide, and barium hydroxide. It's essential that you understand this. Now, let's just go and look at the board. I'm going to lift the camera. Take a quick look at what we have here. All right, let's summarize then. For a reaction to be ionic, there is only going to be a forward reaction. There are 3 things that would make a reaction ionic. Number 1, formation of a precipitate. Know your solubility rules. Number 2, formation of a gas. You should be familiar with carbon dioxide, sulfur dioxide, and sulfur trioxide. You should understand how these relate to environmental pollution and acid rain on the east and west coast. You also want to know H2S, which is either hydrogen sulfide or hydrosulfuric acid. This we'll discuss in the laboratory. Leaving the gases, we then look at slightly ionizable products. Water is the most common slightly ionizable product. It does not split up to form ions. It remains neutral molecules when placed in water. Weak acids do not ionize to any appreciable extent. I'm not saying they don't ionize at all, but very, very few. You should know your 5 strong acids. The 5 strong acids on the periodic table have a pattern: HI, HBr, HCl, H2SO4, HNO3. Make sure you see these when you look at your periodic table. And then we have our strong bases. Strong bases, first family, and the hydroxides of calcium, strontium, and barium. This will get us ready to move on to the next piece of information we'll be learning in chemistry.